Hello Statistics 1 students, week 13 of maintenance. This week I actually dispensed with the first KI. I decided not to do a representation of data. I just decided to go straight into probability so that we could do a few more questions from some of the other sections of the course that we've done, and I feel like we're probably generally doing pretty well with that first section. I might put it back in the weeks to come. The first question today is a probability question. On Saturday afternoons, Mohit goes shopping with a probability 0.25. He goes to the cinema with a probability of 0.35 or stays home. Now, if we add that up, we get what was that, 0.6, so the stay at home should be 0.4. What else? If he goes shopping, then the probability he spends more than $50 is 0.7. If he goes to the cinema, the probability he spends more than $50 is 0.8. And if he stays home, he spends $10 on pizza. And we've got to find the probability that Mohit will go to the cinema and spend less than $50. So what we're going to do is we're going to set up a tree diagram. So we've got shopping, cinema, stay home with 0.4 here, 0.35 here, and 0.25 here. Whoops, 0.25 here. Now, if he spends greater than $50, or he can spend less than $50, and the same here, greater than 50, whoops, greater than 50, less than 50, and this one he automatically spends $10, which I guess we could just rewrite it as less than 50. Now the probability is for this first one is 0.7, which means that is 0.3. This is 0.8, which means that this is 0.2. So that's our tree diagram. Now the probability that he will go to the cinema and spend less than $50 is that branch there, which happens to be 0.35 multiplied by 0.2, which gives us 0.07. Ookly dookly. So the next one, given that he spends less than $50, find the probability that he went to the cinema. So the probability of cinema given less than $50. That is equal to the probability of cinema intersection less than 50 divided by the probability of less than 50. Now, we've already worked out the top, intersection cinema and less than 50, which is 0.07. Now we can see the probability of under 50, there are different ways of getting it. There's one, there's the other one, so there's three altogether. So we just pop them in. The first one is 0.25 multiplied by 0.3. The second one is the 0.07 we've got, and the last one is 0.4. When I pop that into my calculator, I get 0.128. Alright, the second topic is discrete random variables. Rory has 10 cards. We've got 10 in total. 4 have 3 printed on them. 6 have 4 printed on them. He takes 3 cards at random without replacement, and he adds up the numbers on the cards. And we've got to show that the sum, the probability of the sum of the numbers on 3 cards is 11 is 1/2. Okay, well how can we add up to 11? Well, we could get 3, then a 4, then a 4, or we could get 4, then a 3, then a 4, or we could get 4, then a 4, then a 3. I think those are the only ways of adding up to 11. Now the chance of this is, of course, well, how many 3s have we got? 4, and there's 10 cards to start off with. Then we've got 6 of the 4s out of 9 for our second pick, and our third pick will be 5 out of 8. And of course, what you'll find that these other 2 are exactly the same probability, so we could actually just times this first one by 3. But just for completeness sake, I'd say this one is 6 out of 10. This next one is 4 out of 9, and then 5 out of 8. The last one would be 6 out of 10 times 5 over 9 times 4 over 8. Okay, now if we add them all together, or just add one of them and times by 3, we end up getting 1/2. Okay, now we're going to do a probability distribution table for this. So what are the different results we can get? Well, we know that we can get 3, 3, and 3, which is 9. So we get a 9. We know we can get a 10. 3, 3, and 4, so we can get a 10. We've already ascertained we can get an 11. And 12 is the highest we can get. That's if we get a 4 each time. And then we want prob. So here's our table. We already know the probability of 11 is 1/2. Now, let's think about the probability of getting a 12. So 12 we can get by getting 4, 4, and 4. And that is, the probability of that is 6/10 times 5/9 times 4/8. And so that's 1/6. And we've done 11. The probability of getting 9 is also quite easy. That's 3, 3, and 3. And the chances of that are, well, we've got 4, 3, so it's 4/10 multiplied by 3/9 multiplied by 2/8. And when we do this, we get 1/30. Okay, it's my children making all that noise in the background. They're, for some reason, doing a play, and each of them are acting some different... well, I heard Susie Wiles, someone was acting for Susie Wiles, someone was Jacinda Ardern, someone was Trevor Mallard. Goodness knows why. Okay, right, 10. How do we get 10? Well, there are a couple of ways of doing this, of course. We can get 3, 3, and 4. We can go 3, 4, 3, or we can go 4, 3, 4. And each of those ways is the same probability. So we could do 3 multiplied by, let's just try the first one, for instance. That would be 4/10 times 3/9 times 6/8. Okay, and when we multiply that out, 3 by 4/10 by 3/9, that gives me 3/10, I think. Yep, 3/10. So there's my probability table. Now, the next one, event R is the sum of the numbers on the 3 cards is 11, and event S is the number on the first card is 3. Are they independent? That means, so if they're independent, here's the thing. If they're independent, the probability of R given S is equal to the probability of R. Or we can write that out in full. We can say the probability of R intersection S over the probability of S ought to be equal to the probability of R. Now, we can just test this, or again, another way of saying this, right, would be, oh wow, don't do that. Pop that over there. Another way of showing this would be that they're independent is the probability of R given S is equal to the probability of R multiplied by the probability of S. Okay, so that's our condition. Now, probability of R intersection S. Now so this is something that the sum of the 3 numbers is 11. So yep, and the S is the number on the first card taken as a 3. So it's this situation here. We can get an 11 that way. So that probability is 4/10 times 6/9 times 5 over 8. So if we go 4 over 10 times 6 over 9 times 5 over 8, and that gives us 1/6. So I've got 1/6 here. Now, what is the chance of the probability of R? R is the sum of three numbers is 11, 1/2, and S is the first card taken as a 3. Well, the first card taken as a 3 is a 14th chance. But the thing is, 1/6 is not equal to 1/2 times 14th. Therefore, R and S are not independent. Okay. D. Determine whether the events R and S are exclusive and justify your answer. Well, no, they're not. No, they are not. And the reason is because you can score 11 and have the first card be a 3, so they're not mutually exclusive. You can fulfill both of those conditions at the same time. Now we're going on to our permutations and combinations. We've got to write these 11 letters and we're arranging them in a line, and we've got to find the number of arrangements if there are no restrictions. So what I like to do with these is, well, let's write out the word here. R, E, M, E, M, B, R, A, N, C, E. Now let's look at the ones that are repeats of each other. So I've got 3 of those, and then we got 2 M's, and we got 2 R's. I think everything else is different. Now we're arranging them. Now, since the E's are identical, they when they're in the same place, it doesn't matter. Like, I could move this E to there and that one to there, and it'll be exactly the same. So the way we do this is we say, well, there's 11 letters. So if there were no double ups, there would be 11 factorial ways of arranging this. And because we've got some double ups, we divide by those double ups. Well, we've got 2 factorial, which represents the 2 R's, times 2 factorial, which represents the M's, and then times 3 factorial, which represents our 3 E's. Now, when we chuck this into the old calculator, I get a big number. 1,663,200 different ways of arranging those letters that are different. Find the number of different arrangements which start and finish with the letter M. So you can think about it like this: M, and then we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and then M. So if we look at this, we can ignore this and ignore this, and then we're just arranging everything else. So you can see that you've got 9 letters, so there's 9 factorial ways of arranging them, but you'll notice we've still got the E double ups and the R double ups. We can ignore the M's because they're just at the start and finish. Now when we do this, that gives us 30,240. I think. Let me just have a quick check of that. Yep. Okay, now find the number of different arrangements which do not have all 4 vowels next to each other. Well, what I would probably do first is find the number of arrangements that do have 4 next to them, the vowels all together. So what we can do is we can think about the word remembrance and split it up. So we can write all the consonants together: R, M, M, B, R, N, and C. And then we can write all the vowels together: E, E, A, E. Now we can treat all the vowels as one block. So we'll treat this as one letter, right? And we can arrange that. So if we arrange this, you can see there's 7 here and 1 here. So we'll call it 8. Whoops, 8 factorial, and then within this bit here, we're going to divide by 2 factorial and 2 factorial for the m and the r. Then we're going to times the arrangement by 4, because there are 4 ways of rearranging the vowels. I could have A, E, 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 or E, A, E, E, or E, E, A, E, or E, 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 A. Okay, so there's 4 ways of arranging that. So this is the number of ways that we can rearrange. We can arrange it when we want to have the vowels all together. So 403,200. Now, to find the ways where we can't do that, or they're not together, we go the original number that we got for all of the different ways we can arrange it. We subtract the ways where the vowels are together, and that gives me 1,622,880 ways that I can arrange them where they're not all together. Now the last question today, 4 letters from the word remembrance are chosen. Find the number of different selections which contain no M's and no R's and at least 2 E's. Okay, so let's look at the letter. We're going to take our R's out and our M's out. So we go E, E, B, R, A, N, C, E. Okay. So at least 2 E's. So we can have I need to get rid of that R as well, don't I? So B-A-N-C. Okay. Maybe we can even write it like this. We can go E, 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 and then we've got B-A-N-C. Okay. Now, let's consider there's the options that we have. We could get 2 E's and then 2 from B-A-N-C. So the number of ways of doing that is, so that's with these guys, and then you're choosing 2 from here, and you see that there's 4 to choose from, so it's 4 choose 2. If we have 3 E's, then you're choosing 1 from this group of 4, which would be 4 choose 1. Now 4 choose 2 is, what's that, 6? 4 choose 2 is 6. And 4 choose 1, of course, is 4. So I think there are 10 ways that you can choose a selection that contain no M's, no R's, and at least 2 E's. So that could be 2 E's or 3 E's. So 10 ways altogether. Hopefully that makes sense to you guys. Let me know if you've got any questions, and I'll see you next week.